All right, let's dive right in. We're going to explore one of the most violent explosions in the entire universe to solve a really big cosmic mystery, the kilanova's secret. And believe it or not, it all starts with a simple question about where everything around us really comes from. So take a look at any gold jewelry you might have. Where did it come from? And I mean really come from. You might say a mine, deep in the earth. But that's not the whole story, not even close. The true origin story of that gold is, well, it's way more spectacular. It wasn't made on our planet at all. It was forged out there in the cosmos and then delivered here. So the real question is, how? Well, finding that answer means we have to go looking for what you could call cosmic gold factories. We're talking about events so powerful, so incredibly violent, they literally shake the fabric of space-time itself. And in doing so, they create the heaviest, most precious elements in the universe. And the star of our show, the heart of this story, is an event called a kilanova. So what is it? Just imagine two neutron stars. These are the super, super dense, collapsed cores of massive stars. Well, imagine them spiraling into each other at incredible speeds, and then merging. What you get is this cataclysmic explosion, a flash of light brighter than 1,000 regular novas. It's just, wow. And look, this isn't just some cool theory we cooked up. We've actually seen this happen. Back in 2017, there was this gravitational wave event, GW 170117. It was the spectacular, smoking gun proof we'd been looking for. It confirmed without a doubt that these kilanovas are one of the main places where the universe forges all the heavy stuff. We're talking gold, platinum, even uranium. So what's the actual recipe for making gold? It's something called the R process, which stands for rapid neutron capture. Think about it like this. In the absolute chaos of that merger, atomic nuclei get slammed with this furious barrage of neutrons. They get captured so incredibly fast that the nucleus doesn't even have time to decay. It just keeps getting bigger and bigger, building up into the super heavy elements we know and love. It's basically the universe's most extreme pressure cooker. And for a while, that felt like a really neat, complete story, right? Kilanovas happen, they use the R process, they make heavy elements, case closed. But as astrophysicists looked closer, as they really took a census of all the elements in our universe, they realized something just didn't add up. There was a nagging, persistent cosmic mystery. See, the raw process is absolutely fantastic for explaining those elements that are super rich in neutrons. But what about all the others? Does this one single process really explain the origin of every element heavier than iron? The data started screaming, probably not. And this table here, it just nails the problem perfectly. Okay, so look, our models for kilanovas, they're great at explaining how much gold and platinum we see out there. It matches up. But then look over at molybdenum and ruthenium. The models predict we should have very, very little of them. But what we actually observe is a lot. And for years, this Mo-R puzzle, as they called it, was just this massive hole in our understanding. So here's the crucial detail. These specific isotopes, they belong to a special class called P nuclei. Why? Because they have more protons than their stable neighbors. And the R process, which is all about neutrons, it just can't make them. Not in the amounts we see, anyway. So where the heck do they come from? Yeah, this was a major, major headache for astrophysicists. Okay, and this is where some really brilliant new research comes in and proposes a fantastic solution. What if the kilanova isn't just one kind of factory? What if, hidden inside that single incredibly violent explosion, there's a second, completely different kind of elemental forge at work? And this slide just lays out the new idea so clearly. A kilanova isn't just one big uniform blast. No way. You've got the material that gets flung out by tidal forces. That stuff is super neutron-rich, and it's perfect for making gold with the R process. We knew that. But then you have these winds blowing off the central disk that's left over. In that region, intense neutrino radiation is actually flipping neutrons into protons, creating a totally different proton-rich environment. And that place uses a P process to forge those exact elements we were missing. 2 forges in 1. And the key insights, as one of the researchers, Renzo Prez-Cariano, puts it, is that kilanovas can provide a complementary channel for these elements. So it's not about throwing out the gold factory story. Not at all. It's about realizing the factory has a whole second specialized production line that we just never knew existed. Okay, so a second forge exists. Awesome. But how does it actually work? What are the specific ingredients for this secret recipe? What makes it tick?
Well, the research points to three absolutely critical conditions. First up, you need a proton-rich environment. Makes sense, right? Second, you need crazy high entropy, and you can just think of that as maximum chaos. It keeps this cosmic soup of particles super hot and disassembled, so the building blocks don't clump together too early. And third, you need fast expansion. The material has to fly apart really, really quickly to basically freeze out these fragile new elements before they get destroyed again.
But out of all those conditions, this right here is the master switch. It's called the electron fraction, or Ye, which is basically just the ratio of protons to the total number of particles. Now, when it's less than 0.5, you've got more neutrons, and bam, you get the R process, you get gold. But if that intense neutrino radiation can push the number above 0.5, the whole environment flips. It becomes proton-rich. And that's when the second forge kicks into gear. It's this one single tipping point that changes absolutely everything. So let's step back. What does this all mean? Why does finding a second production line inside a kilanova actually matter so much? Well, it's because this discovery helps us finally complete the epic story of where all the stuff in the universe really comes from. The takeaway here is just huge. For starters, it gives us a really powerful solution to that nagging Ma-Ru puzzle. That's a big deal. Second, it shows us that kilanovas are even more complex and even more important to galactic chemistry than we ever thought. And remember, this new P process channel doesn't replace the R process story, it perfectly complements it, adding a totally crucial new chapter. At the end of the day, it just gives us a much, much more complete picture of our own cosmic origins. You know, in the end, I think it's really helpful to think of the universe as having all these different cosmic kitchens. You've got supernovas, you've got the hearts of stars, and as we've just seen, you've got the unbelievably violent chaos of kilanovas. Each one of them has its own unique environment, its own special set of ingredients, its own secret recipes for cooking up the elements on the periodic table. You know, solving this pulsar nuclei puzzle really shows that even in these events we thought we were starting to understand, there are deeper secrets hiding. It really makes you wonder, as our technology gets better, as we get better at actually observing these insane, cataclysmic mergers, what other fundamental mysteries of the universe are they just waiting to help us solve?